So in this problem, we are asked to estimate the rate of rainfall given some rough parameters. And what we mean by the rate of rainfall is we're going to call it R, and it's going to be expressed in terms of delta H, delta T. So this is probably something that you've heard on perhaps the Weather Channel, where they'll talk about the number of inches per hour of rain that has fallen. And so this is going to be kind of a useful metric for figuring out how much rain there is in a given area. And the way we're actually going to express this is delta H is going to be actually delta V, the volume of rain that has fallen, over the area in which we're measuring that volume. And so first what we're going to be doing is we're going to be figuring out what this is. And the easiest way to do that is if we picture this box that I'm going to draw right here. So this box is going to have a base of area A, and it's going to have a height V delta T, where V is the velocity of a single raindrop, and delta T is the time that we're looking at. And so what this box means is, given that rain is falling continuously, this box is going to contain every single drop that's going to fall in this area A in the next time delta T. So if we calculate the volume of water that's in this box, that's going to be exactly delta V. And the way we're going to do that is we're going to estimate the distance from one drop to another drop. And in class we estimated that to be about 10 centimeters. And so what we can do with that is we can draw this little box right here, and this is going to be one drop, and at every other point on this box there's going to be another drop. And so what that means is that if we measure each drop's sort of the volume that it takes up, that is going to be, this instance, this length d, and so the volume that it takes up is going to be about d cubed, because for each of these drops it's going to take up only that next corner of volume. And so then what we can do is we can estimate the number of drops to be equal to the total volume of this box right here divided by the volume taken up by a single drop. And what that's actually going to end up being is we have A times V delta T for the volume up here. And down here we just have D cubed. So that's going to be the number of drops that fall in a given area over a certain time delta T. And so now what we can do is we can estimate the total volume of water that falls in that area. And what that's going to be is that's going to be the number of drops times the volume of a single raindrop. So here what we estimated was the volume that we assume is sort of taken up by a raindrop. So that's the volume where we can say, if there's a drop here, we're going to estimate that there's not going to be any drops in the rest of that area. What this actually is it's the volume of water inside a single raindrop. So it's sort of, if you picture this dot, it's the volume of that dot. And so what we're going to do with that is we're going to take, obviously, AV delta T over d cubed from here. And then the volume of a raindrop is we're just going to say it's 4 over 3 pi r cubed. We're going to assume it's spherical and that it has some average radius r. So now this is going to be the total volume of water that falls in that box. So now all we have to do is we have to take this information about the volume of water and plug it in right over here. So remembering that if r equals delta H over delta T, we can use that equation to get r is actually equal to delta V over A delta T. And now we can use this. This V water is exactly the same as this delta V right here. And what we're actually going to get here is we're going to get 4 pi A V delta T r cubed. And now all of that is the numerator for delta V. And now we're going to plug in 3 d cubed times this right here, A delta T. And so this whole messy expression is going to end up being what our value for R is. So now we can do some canceling, make this simpler. We can cancel out the A terms and the delta T terms. And we're going to get 4 pi V R cubed over 3 D cubed. So now, all we have to do to make sense of this is we're going to have to plug in the values that we estimated in class. So what we estimated was, we said that V, the terminal velocity of a raindrop, was going to be about 10 meters per second. R was going to be 2 millimeters, or about 0.002 meters, or exactly 0.002 meters. D is going to be 10 centimeters, or 0.1 meters. And so all we have to do is plug this in right here, and we're going to get 4 pi times 10 meters per second times 0.002 meters cubed all over 3 times 0.1 meters cubed. So now to make this even simpler, remember that all we're doing is we're doing sort of an order of magnitude estimate. The number that we actually get isn't going to be particularly accurate, but it's going to give us an order of magnitude based on the parameters that we put in. So what that means is that since pi is more or less 3 to an order of magnitude scale, we can actually cancel out pi with 3 and it won't make really any qualitative difference to our answer. So we're going to do that, and then combining these terms, we're actually going to get 40 meters per second, and then we're going to have to deal with these cubed terms. We're going to divide this out, and that's going to give us 0.02 cubed. The units of meters cancel out, and that gives us 40 times 8 times 10 to the minus 6 meters per second for R. Now, all we have to do is multiply this out, and it's going to give us 0.00032 meters per second. And just to change the units around so that that makes more sense to what we think of when we think of rain, that's going to be about 1.15 meters per hour. So probably there's going to be something off with our parameters because this is an insane amount of rain. 1 inch per hour is already like a very strong rainstorm. So 1 meter per hour would be unthinkable. So probably there's going to be something wrong with either our terminal velocity or the radius of a raindrop, or possibly D, the distance between raindrops. But there's going to be something wrong because this answer is very, very